This is section 7.8. In this video, we're going to be talking about convolutions. So suppose that the Laplacian of y is equal to the product of the Laplacian of f and the Laplacian of g. We cannot say that y is just equal to f times g. That's not one of our rules of Laplacians. They do not have this multiplicative property. We can, however, express y as the convolution of f and g. So let f of t and g of t be piecewise continuous functions from 0 to infinity. The convolution of f and g, and it's denoted f star g, is defined like this. F star g of t is equal to the integral from 0 to t of f of t minus v times g of v dv. So for example, if f of t is equal to t and g of t is equal to t cubed plus 1, that convolution is equal to the integral from 0 to t of f of t minus v. So that's just f of t is t. So f of t minus v is just t minus v times g of v. So we plug in v into our g equation here and we get v cubed plus 1. Now we calculate that integral with respect to v. So first we have to multiply everything out. So we get tv cubed plus t minus v to the 4 minus v. And then we integrate with respect to v. So this is quite easy because we just get to act like t is a constant. So just a bunch of power rules going on here. And then we evaluate from 0 to t. So in all of these instances, if I plugged in 0 for v, it would just go to 0. So all I have to do is plug in t. So I get t to the 5 over 4 plus t squared minus t to the 5 over 5 minus t squared over 2. And simplified, we get a final solution to that convolution as t to the 5 plus 10t squared over 20. So that's how you can do a convolution of two functions. Here are some of our rules of convolutions, why we've defined it as such. If f, g, and h are all piecewise continuous, then we get that the convolution of f and g is the same as the convolution of g and f. We have this distributive property, associative property, and multiplication by 0. So all these properties hold, and that's part of what makes convolution such a good method. Here's our work with Laplacians. The Laplace of the convolution of f and g is equal to the Laplacian of f times the Laplacian of g. And that's really why we've defined convolutions as we have. The inverse Laplace of the Laplace of f times the Laplace of g is just equal to f star g, or the convolution of f and g. That will be very handy moving forward. So our first question, use the convolution theorem, that's this, to solve the initial value problem y double prime minus 16y is equal to some function g of t, where y of 0 equals 1 and y prime of 0 equals 4, and g of t is piecewise continuous and of exponential order. We always need that when we're taking Laplacians. So y double prime minus 16y is equal to g of t, and we're just going to take the Laplacian of both sides. And then, as we always do, the linearity principle is going to let us break that up. And we've taken the Laplacian of y double prime enough by now. We should know it looks like this. So we can take out, we still have this s squared Laplacian of y. Y of 0 is 1, and y prime of 0 is 4. And that comes from the question there and there. So moving forward, we're going to get this Laplacian y factored out. So Laplacian of y was multiplied by s squared and minus 16. So that's what's inside your brackets there. On the right, we still have the Laplacian of g, and we've moved over these other bits, this minus s and this minus 4, as plus s and plus 4. So dividing both sides by s squared minus 16, we can finally isolate the Laplacian of y. And on the right, we have the Laplacian of g divided by s squared minus 16 plus s plus 4 divided by s squared minus 16. We can cancel out s plus 4 in the numerator and denominator here. And then we can calculate the inverse Laplacian. So we have the Laplacian of y on the left here. We just want to have y on the left. So we have to take the inverse Laplace of both sides. Now here's where we can finally apply our convolution theorem, because we have the inverse Laplacian of some product of functions. And just to finish up what's on the right here, we know this inverse Laplace is, well, it's the inverse Laplace of 1 over s, which would just be 1. But since it's been shifted over by 4, we have to multiply that 1 by e to the 4t. So it's e to the 4t is that inverse Laplace. But now back to the convolution theorem, we know that the inverse Laplace of this product is just the inverse Laplace of each individual piece convoluted with each other. So the inverse Laplace of 1 over s squared minus 16 from the back of the book is the hyperbolic sine, or 1 over 4 times the hyperbolic sine of 4t. And the inverse Laplace of the Laplacian of gt, well, that's the inverse Laplace of a Laplace. So that just gives us g of t. And then by our definition of convolution, we know what integral we need to take. But for this example, we have to stop here because we don't know what g of t is. And note, we would need to put 4 times t minus v in that bracket. So it should actually be the integral from 0 to t . Because it certainly doesn't make any sense to be integrating with respect to t when t is one of your bounds. And if we look back at our definition of convolution, we plug in dv, g of t, and f of t minus v. So that's where those values are coming from. So this is our actual final answer. Now, let's use the convolution theorem to solve this. The Laplacian of 1 over s minus 2 times s squared minus 3s plus 2. So we can factorize that denominator as 1 over s minus 2 squared times s minus 1. Now this is equal to the Laplacian of a product, which is what we like. It's 1 over s minus 2 squared times 1 over s minus 1. So if we were to take the inverse Laplacians of these pieces individually, we would get t e to the 2t convoluted with e to the t. And our convolution theorem says that this convolution is equal to the Laplacian of these two values multiplied together. So now we're going to actually calculate this convolution. So it's t minus v times e to the 2t minus v. That's what you get when you plug in t minus v for t here, convoluted with e to the v. Now expanding that out, we get t e to the 2t minus v minus ve to the 2t minus v. And now this looks rather complicated, like there's a lot of variables here, but remember, we're only integrating with respect to v. So if we're looking at the integral of t e to the 2t minus, not 4, minus v with respect to v, well, note that this is the same as the integral of t e to the 2t times e to the negative v with respect to v. And this whole t e to the 2t business is just a factor. So when we integrate that, all that happens is everything stays the same, but that negative comes out front. So that's how we get this first piece of the integral. We're going to evaluate negative t e to the 2t minus v from 0 to t. On the right, we may have a slightly trickier time because there's a v factor here and a v in the power. you should immediately think integration by parts. So we would let one of our values be v, and then the derivative of that. Our other value would be e to the 2t minus v, and then the integral of that, which we just showed to be negative e to the 2t minus v. So when we plug those values in using our integration by parts formula, we're going to get negative v e to the 2t minus v evaluated from 0 to t minus the integral of this right here, negative e to the 2t minus v dv. So when we calculate that integral, again, all that happens when you calculate that integral is the negative comes out front because that e to the 2t is just a factor. So this is now what we are going to evaluate from 0 to t. Well, when we plug in t, we get negative v e to the 2t minus t, which is equal to negative v e to the t. But wait, because we need to plug in t for both of the v's. So it should be negative t e to the t. And then this negative sign here will make that positive. So that's how we get the first piece. Now, when we plug in t to the second component here, we get e to the 2t minus t, which is just equal to e to the t. That's our second piece. Now, what happens when we plug in 0? Well, if you plug in 0 for v here, that just goes to 0. But you can plug in 0 here, and you'll just be left with negative e to the 2t. Now, canceling out terms, we're left with t e to the 2t plus e to the t minus e to the 2t. Okay, for our final example, solve the following integro-differential equation. Now we call it that because there's an integral and there's a derivative in here. But we now have the pieces to solve such an equation. It is initial value. We need to know that y of 0 is equal to 0. So this is the problem. But we note that the integral from 0 to t of y of t minus v is actually a convolution. If we go back to the definition of a convolution, this is just the convolution of y of t and 1. Well, let's take the Laplacian of both sides. Use our linearity to get this Laplacian of 2 out, because we can actually solve that separately. It's just 2 over s. And now we can worry about this Laplacian of y convoluted with 1. Well, our rules say that that is equal to the Laplacian of y times the Laplacian of 1. The Laplacian of y we don't know the solution to, but we know the Laplacian of 1 is 1 over s. And now we can move all the Laplacian y terms to the left and isolate it. So it's equal to 2 over s times this value, s minus 1 over s. Well, simplifying that, multiplying through by s, we just get that the Laplacian of y is equal to 2 over s squared minus 1. That is itself a product. And when we take the inverse Laplacian of this to get y, we have to take the inverse Laplacian of the right side. And we're quite pleased to see that this is the inverse Laplacian of a product of two simpler things. So that's the inverse Laplacian of 1 over s minus 1 convoluted with the inverse Laplacian of 1 over s plus 1. Now we know those inverse Laplacians by now. That's just e to the t convoluted with e to the negative t. And now we finish by solving using our definition of convolution. So this is e to the t minus v times e to the minus v integrated from 0 to t. Well, those, when we multiply them, we can just add the exponent. So we get e to the t minus 2v. And now when you integrate that, remember that e to the t minus 2v is equal to e to the t times e to the minus 2v. And this e to the t is just viewed as a factor at this point, just a coefficient. So we're really just looking at what this integral is, which means we're going to have to divide by that -2. So that's where this -1/2 comes out as a factor. The 2's actually cancel, and we're just left with -e to the -t plus e to the t. Well, how does that happen? We have -e to the t minus 2v. We start by plugging in t for v, so we get -e to the t minus 2t, which is equal to -e to the -t. That's your first piece. Secondly, we're going to get a positive e to the t minus 2 times 0, which is just equal to e to the t.